Okay, so I'm going to try it this way now. Um, so this is where we left off, and I think I probably rushed through this last slide, so might as well just start with this one again. Instead of animating it, I'll just talk through the whole thing. So one of the most important things is that dielectrics always increase the capacitance, right? Kappa is always greater than 1. So a very common question is, what would happen if I put a dielectric in while it was connected to a battery? Okay, so remember, a battery's job is to keep the voltage and E field, right? Because the voltage is E times D. And so if it keeps the voltage constant, then it'll keep the E field constant. So the dielectrics, there's an induced charge on the surfaces of the dielectric that are acting to decrease that electric field in there. So the battery's like, no, we need that E field constant. I'm going to send more charge your way. Okay. And that will, bring that E field back up to where it was originally. Okay. So what just happened? It put more charge on those plates. And the whole idea about the word capacitance is it sounds like capacity, right? So an increased capacitance means it can hold more charge for a certain potential difference. Okay. And so what I have here is that just how much that capacitance increases by, right? By that factor of kappa. And if we start out with a certain amount of charge, certain capacitance, and certain voltage, right, we know that voltage is going to stay the same. And so if our capacitance increases by a charge of kappa, our charge increases by by a factor of kappa. So that's how we got that. Okay, let's keep going. Now I think I'm going to present, and I disappeared. Okay, that's fine. Just kidding. Boom, boom, boom. Done. And aha. Okay. It says reminder series in parallel. So you might say, what do you mean reminder? We never did that, except I did in a video that's in my playlist. So the spherical and cylindrical capacitors also has series in parallel. So we talked about series in parallel at some point when we were doing springs. And so then I did a whole thing on capacitors, but here's a reminder. So take a moment to think which one's which. Okay, good. Hopefully you guessed right. Okay, you know which one's which? Okay. When you look at these equations, and you're going to see these very similar equations in resistance, except they're going to be switched for series and parallel. But one of the things that's important to realize about the structure of these equations, and it's obviously very easy to see with this one, the equivalent capacitance here is bigger than either of the initial capacitances, okay? And that's going to happen in a parallel configuration. And I'll give you some intuitive building things on that in a second. But then just looking at the structure of the mathematics of this, when you have an equation that looks like this, your equivalent is going to be less than either C1 or C2. Okay, so if we had, for instance, a 12 microfarad and a 6 microfarad capacitor, just showing you some like actual numbers, okay, these are what those would end up looking like. And you see that the equivalent capacitance for a parallel setup is bigger than either the 12 or the 6, and the equivalent capacitance for a series is less than either the 12 or the 6. And so here's why. Okay, I'll go back. So look at the parallel. What this really is like is think about all the charge that's building up on these capacitor plates. I've just given you 2 plates to be able to I can't easily like stop and go back. That's very sad. Okay. There's more area. That's the words I'm looking for. There is now more area for your charge to sit on. Ooh, this is a fantastic video. Sorry about this, guys. So you can kind of look at it like this. It's like a bigger area. And so it can hold more total charge for the same potential difference. Okay? For the series, look at it this way. It's like increasing the distance between the plates. So now instead of this or this, it's like we had a capacitor with this, which is a big distance. And if you have a big distance, then you're going to have a smaller capacitance, right? And just remember, if you're big distance and you've got you're trying to hold things that want to be together apart, and so it's not going to like that. Okay, so okay, so now I'm just taking these away. So let's talk about voltage. When we look at these circuit diagrams, and next unit we're going to do circuits in all of their glory. This is sort of like getting you into it a little bit. A wire, all along a wire, has the same potential, right? Because remember we talked about wires being equipotentials. So I'm going to draw some blue lines. Okay, so all the things in blue are at the same potential. And so we stop when we get to a component like a resistor or a capacitor or an inductor at some point or a battery. So all along any wire that's attached to each other is the same potential until we get to the component. Then, right, if you look at the bottom half of this, you can see that those green ones are at a different potential. And the difference between the blue and the green's potential is the potential difference across the capacitor. So you can see by the way we drew it, that those are, my gosh, these are horrible. I should have shifted that down. God. You can see by the way we drew it that they have the same potential difference across them. And that is the important thing about things in parallel. Okay. This little color coding when you're drawing on circuit diagrams is actually a super good strategy that I will encourage you to do next unit as well. Okay, so what did we just say? Parallel. It means that it's the same potential difference across them. And you can also imagine that the total charge, Q1 plus Q2, is going to be the Q total. Just because, if you think about charge coming in this way, right, it's going to add up. And then this guy is going to add up. So Q1 plus Q2 is Q1 plus Q2 is. Okay, so I did actually figure out how to pause. So I don't know exactly what I just said because I just had to take a phone call, but here we are. Parallel. Okay, I think we finished parallel. I hope. So now in series, let's see. There we go. So now let's draw these blue lines again. So we're drawing this wire here, right? It's like the blue part is connected to the top part of the battery, right? So a high voltage, and the bottom, the green part, is connected to the other side of the battery, it's the 0 volts, right? So there's my blue, there's my green. Hopefully you see that they're not they don't have the same potential difference, that there's something in between, right? And so if you want to think about potential as like, as an elevation kind of thing, it's like this is the top of the stairs, and then you go down a couple stairs, and then, right, by the way, this is the same level stair, and then you go down another, right? So this is like 2 steps, 1, 2, right? Whereas here, it was like 2 people on the same step, and it was just 1 step, 1, 2. Okay, so what you see here is that the voltages add up, right? So it's the same total distance or same total potential difference between the blue and the green, but you're taking some steps. Voltage 1 plus voltage 2 is the total voltage. And they're going to each have the same charge, because say you drew a little box around here, it would have to be neutral. So it would have to be like plus Q minus Q, plus Q minus Q. Okay, there we go. That's series and parallel. All right, what's next? Yes, some interesting situations to think about. So, what do you think? So this is a capacitor half filled with a dielectric. So what do you think the total capacitance of this capacitor is? So why don't you pause and think about it and then come back. And now here we are. Okay, you can think about this one too. What if it was half filled this way? So pause and think about it. Looky here. These look like two capacitors, one filled with air, one filled with a dielectric. And the question is, are they in series or parallel? Sorry, I just gave it away. They're in parallel. How do we know? We know because this one has a potential difference of whatever, and this one has the same potential difference. So if they have the same potential difference across them, they're in parallel. Okay? So these same across each. But what are the kind of capacitances? Well, this capacitor is epsilon naught. So remember, it's just epsilon naught A over 2, or sorry, epsilon naught A over D, right? But here, it's just this whole area over 2 is the area of this capacitor, right? The one with just air. And then the other capacitor is kappa, epsilon naught A over 2D, okay? And because it's in parallel, they add. And so it's C naught plus kappa C naught. And so that's what you get. Okay. Here, can you see that these are capacitors in series? That the total voltage, the total voltage is this voltage across the kappa C naught and then the voltage across just the C naught. And so then we can write C naught, epsilon naught A over, in this case, it's a D over 2 is the distance between the plates of the capacitor. So then we get this guy. This is just, obvious math that you can muddle your way through. But, that's the important part is that inverse equation. All right, what else? Ooh, what will happen if I put a metal slab inside a capacitor? Bum, bum, bum. Metal's a super good dielectric, right? It's completely polarizable. So what will it look like? All right, let's take a look. So here's the top plate, here's the bottom plate. When I put a metal slab in here, right, with any dielectric, it'll be more negative on this side, more positive on this side. With a metal, it's completely negative and positive on this side with as many of those charges as there were on the plates. Okay. So when you look at this, all of a sudden now it's equivalent to this, which is two capacitors just filled with air with these dimensions. Okay. So it's one thing for me to just show you a picture and say, oh, isn't that obvious? Work through it yourself. Then I think you'll see it. There's the rest of the calculation. Again, one of the things you would want to check is, does this make sense? The limit as A goes to 0, right, is the limit of just this being a normal, boring, air-filled capacitor, in which case you get epsilon naught A over D. So that sounds good. So that's always important to check, when kappa goes to 1, so it's just air, or when, certain distances go to 0, or the full thickness, you should make sure that whatever funkalicious answers you get for these equivalent capacitances, that they make sense in the limiting cases. So one of the things that you sort of just say here is putting that metal slab in here basically just reduces the separation. So do you see that the difference is D minus A? Okay, so putting a metal slab here just reduces the difference. And again, take that to the extreme of A going to D, right? What would happen? If A went to D, you would have like this infinite capacitance, right? This is just a capacitor. Or it's just, sorry, it would just be like a slab of conductor. Okay. So, I think that's it. All right. That's all she wrote. Let me turn this off.